Hey everyone, we're starting into chapter 24 here, which is capacitance. We looked at capacitors today and saw what they were able to do, and the capacitor in this picture is located right here, right where the camera flash is. Inside of cameras, they have devices that allow you to build up charge and then release that charge in a large flash, kind of like we saw today in our exploratory lab, where we charged a capacitor. We piled up charges from an energy source like a battery, and then we neutralized the capacitor by discharging it and sending the charges through a light bulb. So we can see that there's energy associated with separating charges, and we can separate them in these little devices here. These little devices like here, here, and here, all of these things in this circuit board are capacitors. So we've got large capacitors, we've got small capacitors. They're all there to store charge and to store energy for us. So the definition of capacitance is a source of potential difference. Basically, they're two plates. There's two plates inside of any capacitor you find, and those plates are separated by a certain distance. And what we do is we can start off with the plates neutral. So we start off with neutral plates here. And if there's neutral plates, there's no field set up because one plate isn't charged more than another. But if you are able to do some work, and we saw that we could do work with a battery, we could take a charge and move it from one plate to the other. So if I take this positive and I move it over to this plate, what happens is that this plate gains an extra positive charge, and this plate has lost a positive charge, so it becomes negative. Or you could do vice versa. You could move electrons from one plate to the other. But now we can see that each plate is now independently charged. One is now positively charged, and one is negatively charged. We could do more work now, but it's going to take a little bit more effort. The reason it's going to take more effort is when we separate charges, what we set up are electric fields. And so there's an electric field now set up between these two plates, pointing from high volts to low volts. And if I try to take another charge and move it from one plate to the next, I'm going to have to put in more energy and put in more work. So if I do the work, I can make one plate completely negative and make the other plate completely positive. So I've stripped all the electrons off of one plate and pushed them onto the other plate. It takes energy to do that, and when we do that, we have now set up electric fields. And since there's an electric field between the two plates, that means there must be a potential difference. So what we did with these today in class is we had charged plates inside our capacitors, and then we hooked those capacitors up to a light bulb or a generator. And like we saw in the equipotential lab, if there's a potential difference from high to low, charges will flow from high to low, and as they go through devices, they can either give off light, or in the case of the generator here, it was able to spin the generator. So separating charges in capacitors puts energy in the capacitor as well. So we had you graph a couple things. We looked at all the energy we had in a capacitor and compared that to the potential difference we set up with each of these plates. We kept charging these capacitors to more and higher potential differences, which means there was larger and larger charge separation on each plate, and we were able to see that charge was related to voltage. And if we relate charge to voltage, when we graph that, we said that the area under the curve had meaning for us. The area under the curve here, if you look at the units, that should give you joules. So we knew there was energy in the capacitor based on our observations. So the area under the curve tells us the energy that's involved in moving charges from one plate to the other. But remember, there's two things we always look at for a graph. We don't just look at the area under the curve, we also look at its slope. So if we look at our slope of a graph like this, charge per unit volts, we get a coulomb per volt, remembering that volts is joules per coulomb. So really what we get here, when we get the slope of charge over volts, or this ratio of charge per volts, you get coulomb squared per joule. Okay, which again doesn't seem to make much sense, but what we call that is farads. So a farad is a unit of charge per unit volt, and that is the definition of capacitance. So like we said, it takes work to separate the charges, to create a potential difference and increase potential energy of charges. That work can come from a battery supplying the energy, or a generator can lift the charges to create that potential difference. And since charge is proportional to volts, the proportionality constant here we're going to call C. C is our capacitance. It's our charge per unit volt ratio, or like we had, coulombs per volt. So instead of saying coulomb per volt or coulomb squared per joule, which again is a big mouthful, we call that a farad in response to Michael Faraday. A farad is the unit for capacitance. Today in the lab you had two capacitors there. The large capacitor, like in this one, says it is 220 microfarads to store lots and lots of charge. Capacitance is again in small units like microfarads or millifarads. And that even smaller capacitor we had in the lab was actually 1 full farad. So let's look at this unit of a farad. Like, why are we making things in microfarads? Why aren't we just building capacitors that have large amounts of capacitance? Let's say we had a sphere. In the sphere we were going to store charge away from the ground. So we're going to charge the sphere and see if this sphere could have a capacitance of 1 farad. So what would that take? Well, capacitance is charge per volt. And the voltage of a sphere, that's an easy one. Voltage of a sphere is a point charge. The capacitance is going to be charge per kQ over R. Well, if you look at that, there's charge in both places, and we can knock out the Q, which means the capacitance of just a single sphere isolated from the ground would be the ratio of its radius over the Coulomb constant. So if I wanted a capacitor that had 1 farad of capacitance, I could put 1 in for my farad. I know my Coulomb constant, 8.99 10 to the 9th. That means the radius of the sphere that I would need to build a 1 farad capacitor. Solve that out, and the radius would be 8.99 times 10 to the 9th meters. So I would have to have a sphere that has a radius that is 9 billion meters wide. That's wider than the entire Earth. So when we build capacitors here, having a 1 farad capacitor means that you can store tons of charge on a certain area. But we had a 1 farad capacitor in my hand, and right here we're saying a sphere needs to be as larger than the Earth. So how do we even do that? Well, let's try a couple examples of finding capacitance for different shaped objects. So let's go with parallel plates. If we go with parallel plates, you can see that one plate will be positively charged, the other plate was negatively charged, and between those two plates we set up an electric field. Since there's an electric field set up, electric fields point from high to low voltage, so as soon as you see an electric field, know that we must have a potential difference. The potential difference is there, which means we have a voltage. So if I want to solve for the capacitance of two parallel plates, this is what we need to do. Alright, so let's start off with two parallel plates having an electric field, and the plates are separated by a distance d. Well, if I want to solve for electric field strength is dV over dr. Or in this case, if I wanted to rearrange that and solve for my voltage, so electric field strength is dV over dr, and if I want to solve for the capacitance charge I can store between these two parallel plates, I need to know my charge per unit volt. Knowing the electric field strength is good, but I need to find the voltage so I can find the capacitance. Well, if we use Gauss, E dot dA equals charge enclosed over epsilon 0. And if I want to make a Gaussian surface here, why don't I make a Gaussian surface that wraps up the positive charge on this plate? So really, the area that I've got here is just A, so E times A. And since I have charge over the entire area, that means I've got sigma, and that means that the area of my Gaussian sphere really doesn't matter. So the electric field from a parallel plate, again, is just sigma over epsilon 0. It's a constant. Well, let's put that into our electric field equation here and solve for volt. So if I want to solve for potential difference, I put in my electric field, which is charge per unit area over epsilon 0 times our displacement. The displacement from one plate to the other here is going to be this distance d. So I'll put in d for the distance between the two plates. Now that I know the voltage between the two plates, I can put that in my charge per unit volt ratio for capacitance. And what you end up getting is Q all over Q times D over area times epsilon 0, which means I can knock out the Q here and solve for capacitance. Rearranging that, you get the capacitance for parallel plates is area times epsilon 0 over. So what that's meaning is the capacitance is just a factor of its geometry and how you make the capacitor. It has absolutely nothing to do with the amount of charge or the voltage that you put on the plates. It's a unique setup. In this case, for parallel plates, to have a large capacitance, you've got to have a large surface area for your plates, and you want to have a very small distance between your two plates, which we'll talk about why having really close plates may not be the best situation to create a capacitor. But we can create large capacitances by having large plates, having them very close to each other, and we don't have to make spheres that are as large as the Earth. The last example we have here is finding a cylindrical capacitance, charging one cylinder positively and the other cylinder negatively. If we want to find the capacitance, we got to do the charge per unit volt, which means using dV equals negative E dot dr again to solve for the electric field that's set up between these two cylinders here. So again, use a Gaussian surface, create a Gaussian cylinder that is going to surround that inner charge, and find the electric field away from that cylinder. When you do that, put the electric field into this equation, find your voltage, put your voltage in the capacitance equation, and solve for the capacitance of your setup. So I'm going to have you guys try this one on your own, and we'll talk about it when we see each other in class.